So, I like that sound. Yeah, what's up?
It has to do with my actual test, but I have to show you my answers. Were these right? They're just in the wrong spot?
Almost.
Well, this one.
That's wrong, but that should be there. Yeah.
Oh.
This is the idea. At least come up with what we can multiply it to be. So the answer to LCM will almost always be bigger than either of the numbers. The GCF will almost always be smaller than either of the numbers.
Oh, dang.
Yeah.
So close.
Okay. So let me put something up here, see what you guys think about it. Well, I mean, actually, let me just do this. Okay. What does that mean? There's a lot of different ways you can tell me.
4 divided by 5.
I love it. Cool. There's a good start. 4 divided by 5. And of course, what would be weird to your student who you've progressed through everything we've progressed through when you put this up here? 4 divided by 5. What's weird about that?
They're always 4 smaller.
Yeah, can 5 go into 4? Can it fit in? No. Shit. So, I mean, that's the first level of freakiness with fractions, correct? The answer, it cannot be 1 or more. It's got to be less than 1, yes? All right, so that's one thing. This is definitely less than 1. 5 can't go into 4, really. In fact, this would be silly to do, right? 5 goes into 4 no times. Remainder 4. Okay, yeah, that was great. Okay, thanks so much. Right? That didn't really do anything for us. Okay. So let me do this. Let's kind of build our way up to this kind of fraction. What is this a fraction? Is that a fraction?
Yeah.
Yes, it totally is. In fact, every whole number is a fraction, because every whole number I can put it over 1, correct? And this is just the whole number, what? This is 2. Okay. Why is this 2?
Because there's 2 groups of 3 and 6.
Say again?
Because there's 2 groups of 3 and 6.
I love it, kick ass. 2 3s are required to add to be 6, correct? So watch, I really want this to make sense. We're going to do a deep dive into what the shit a fraction by itself means, yes? This fraction represents the number of these that it takes to make this, yes? And that's kind of a different way to put it. So 6 divided by 3 is 2 because 3 times 2 is 6. It takes 2 3s to make 6. So real quick, before I get to the freaky fraction, what would this represent? What would that represent according to the way we're looking at it right now?
5.
And to tell me words. It's the number that, the number of what?
Oh, like.
Yeah, so this would be the number of 4s
In 20?
to add to be 20, correct? Jeff, you can do it. Now, is that the normal way we say this? Would a normal human ever say this necessarily when they're faced with this problem? No. But does this make sense? Right? And again, this is why the answer is 5, because if you add 4 to itself 5 times, you get 20. Or more directly, repeated addition is multiplication. 4 times 5 is 20. Okay, I like it. Now, does it, and think about this, it really doesn't matter what numbers I put here. It will kind of be able to be discussed like this. So let me give you, here's the first freaky one. me see, all right, let me do one little thing. I knew I was gonna get this. I just kind of created this way to look at things this morning. So you'll forgive me for something. I could have turned this around, yes? I could have said, how many 3s does it take to make 6? Or I could have said, what did I say? Yeah, I could have said, how many, what does it take 3 of to add to be 6? Yes, I could have said it that way. If 2 groups of 3 make 6, then 3 groups of 2 make 6, yes? I could have said it either way. So this could have been the number of 4s to add to be 20, or, what do I want to say here? What does it take 4 of to make 20? Cool. So this one would be, what does it take, this number, 1/3, what does it represent? It represents the number that it takes 3 of to make 1. And there's no better way to write it, because this is a definition of what this number actually is. So 1/3, I can't do shit with it. Nothing substantial. If I try to long divide it, I get 1/3 back. Yay, right? But at least I can say what it means. It is the number that it takes 3 of to add to be 1. Right? Okay. So if we all want to go somewhere and we need some money, and you got 1/3 of the money that we need, and you got 1/3 of the money that we need, and I got 1/3 of the money that we need, do we have enough money?
Yes.
We do, because 1/3 plus 1/3, 1/3 equals 1 monies that we need. Just to use neat grammar. I love it. We got the 1 monies. Oh, thank you. I don't know. Let me stop for a second. Has anybody ever thought about 1/3 like this? No. And I understand. Does it make any sense? I mean, this is the way, again, what am I trying to do? I started with stuff we would have done before. Didn't we do division of whole numbers? And you would have done it with students. So what do I keep talking about? Every time we get to a new topic, what do I always try to say? You want to build the new topic on stuff they're already familiar with. Yes? Okay, I like it. Okay. So this is definitely less than 1 because it takes 3 of them to make just frickin' 1. Yeah, I like it. So let's come back. What about this then? What does this mean? Hold on. What does that mean? So you can answer it 2 different ways based on
one less than whole, or
All right, I kind of see what you're saying. It's like 1/5 away from whole.
1/5 away.
But interpret it the way we just interpreted everything else. It represents the number. So one way you could say it is the number of.
The number it takes 5 to make 4.
Exactly. What does it take 5 of to make a 4? Yes. This is the number of 5s needed. Of not 5s. You say it's better. This is what it takes 5 of to make 4. Okay. So I just need to work on my putting the sentence together correctly. There are multiple ways to look at this, and there's a certain way that is a broad interpretation for all fractions, and that's the way right there. And real quick, all right, now watch. I want you to see this. All right. All right, there's 4, yes? Now what if I break into 5 parts? He says 1, 2, 3, 4, and then 5.
Yeah.
Break it into 5 parts. How big is each part? 1/5, 11. So this is 1/5. This is 2/5, 3/5, 4/5. This will be 5/5 And what does this mean? This means how many 5s does it take to make 5? It takes 1 5 to make 5. And so forth. So now watch. 4/5 is right here, yes?
Yeah.
And we just said it takes 5 of these to make 4, right? So here's one of them. If I do another step up of 4/5, where do I end up? 4/5, and then I go 1, 2, 3, 4 more. I go one more step of 4/5. Where would I end up?
1, 8,
I don't need a mixed number, but I appreciate it. 8/5, right? So I love it. You're right. Mixed numbers we're going to talk about in a bit. This will be 8/5, yes?
Yeah.
If I do another step of 4, 12/5. If I do another step of 4, right? 1, 2, 3, 4, right? 16/5. And then one more step of 4, 20/5, which is 4, right? So it took 1, 2, 3, 4, 5 of these to make that. I love it. I'm not saying, oh, that clears up all your fraction problems, but I don't know if you've ever discussed fractions like this. They are weird, of course. We don't use them very much. No. We use them more often, but we're used to like a half and a fourth, maybe, and that's about it. It's 1/4 to 3, and we're like, so you understand fractions? No, it's not 3/11 till 3. I mean, what the shit? I don't, right? But we do have some fractions we use every day. How you guys feeling about this so far? Okay. Some of you guys might be bored. You love fractions. I don't know if anybody's in that boat. Okay. Now, let me see. Where are my notes? Okay, come back to my notes. I went off script there for a minute. So let's look at some more visuals. This is one possible visual here, the number line, right? So let's look at a different kind of visual that you should immediately be familiar with, I would think. All right. What fractional part of it have I shaded in? 3/4. Okay, this is your standard visual of a fraction, right? So how many pizzas? So the weird way to say this is how many pizzas are left if I ate that piece? There's no whole piece. What are you talking about? 3/4 pizzas are left. I like it, right? Now what was key here? What's wrong with this picture here? Let me see. Well, that's really wrong, Jen. Oh yeah, I want that. Yeah, I want that. 1, 2, 3, 4. Good job. Here we go. Yeah. Is that 3/4?
No.
Why not?
It's not obviously.
Not evenly distributed.
Yes, each part has to be equivalent, right? Each part has to be equal to the other parts for this to make sense. This would not be 3/4 of the pizza, right? I like it. Okay. So, here's kind of a weird, let me show you this. This is a little bit strange, but see what you guys think. If I did this to represent 2/3, somebody cool with that? Looks like a ladybug or something. That represents 2/3. And then I did this to represent 1/3, yes? Can you see why a student might say 1/3 is bigger than 2/3? So here's the thing, do you guys see that? Okay, does anyone understand? Obviously we all know that's wrong. But look, isn't that bigger than that? So what's this? I told you this is a little weird. But this is like, does 1/2 mean the same thing in every situation it's used in? Right? If I got 1/2 of Jeff Bezos's wealth, would that be equivalent to 1/2 of my wealth? What do you think? Just take a guess. It's got the same first name, but that's about it that we share, thankfully. Well, I don't know. No, thankfully, I'll stay with that. Right? Is everybody with me?
Yeah.
I really want this to make sense because I'm about to say something weird. 1/2 does not always equal 1/2 because it's always what it's based on. But the idea of 1/3 of something is always the same. Yes? Okay. So this, drawing a picture like this and drawing a picture like this is so evil, because this is like Jeff Bezos, and this is like, well, that would be me really, but you can't really see that, but that basically sums up. Do you guys understand what I'm saying? So when you're talking about comparing fractions, they have to come from the same picture for it to make sense, yes? Because otherwise the size of the picture sort of clouds the idea. Okay, I like it. Are you guys with me? Okay. This is the kind of mistake people make with percentages. 10% is not always equal to 10%. It depends on what it's based on, right? Okay. Let's do this. Yeah. So I kind of did this earlier, but let me come back to this. If I broke this up into B equal parts, from 0 to 1, break it up into B equal parts. It should be an easy question. What would this represent? What would this be? Break this up into B equal, like 5, 6, 7 equal parts. But B, I'm not telling you what I did.
N over B.
Say again?
N over B.
I like what you're saying, but this is the first step, so it'd be 1 over B. Right? You guys with me?
Yeah.
Now, is that cool? Everybody with me? That's exactly what we did earlier, the 4/5 thing, right? And again, don't let that, I know B, so again, if I broke it up into 3 equal parts, what would this be? 1/3, that's all I'm saying. I'm just not telling you this is 3, I'm just telling you it's something, I'll call it B. Could be 7, could be 82, okay. What if I go in until I get A steps in? And that's what this is. What would that fraction be? What would this be?
1 over 80.
So again, if I had 5, right? And I take 3 of these steps in, what is this? 3/5. So if I have 1 over B, if each one is 1 over B, and I take A steps in, A over B. Okay. Let's stop for a minute. How many steps would it take for me to get here?
B.
Yeah, it would take B steps, because then this would be B over B, which of course is 1, right? And that reinforces the idea 1 over B represents the number that it takes B of to get to 1. And we just said that. If I take B of B's, I get to 1. Okay, maybe a little bit. Okay. I can still sense a lot of fraction hatred, but that's okay. It happens. Okay. This is good. Let me do this. This is a little bit out of order, but there's no really great place to shove this in, so let's do this now. It's gonna sound a little strange at first, but oh well. Trust me, this has to do with what we're talking about. What is x plus x?
2x.
Holy shit, 2x, right? What is 2y plus 3x? Sorry, 2y plus 3y. Did something a little too early. 5y. Is everybody so far? What is the idea that we're talking about here? Like terms. Yes? Now this is huge for fractions. This is a big realization to make. Here's the last thing I'll say with the x's and y's. What's x plus y? Why is it not xy? What does xy mean?
They're multiplying.
Multiplying. It's not what it's asking for. What is x plus y?
X plus Y.
There you go. That's the answer, right? If I said simplify this, you would just circle it. You go, it was done before you gave it to me, right? Or you wouldn't have to do that. All right, so far so good? So the idea of like terms is pretty straightforward. That is all adding fractions is based on. That's it. Right? So tell me this. What is 1/3 plus 1/3? Yeah, 2/3. Because I got one of these plus one of the same thing is two of those crazy ass things. Right? What is 2/7 plus 3/7?
5/7.
Holy shit, right? Again, this is 2 of these plus 3 of these is 5 of these. And then now we hit the problem spot. What if I do 1/3 plus 1/7? Are those like terms? No, right? This is the same thing here. I have one of these and another one of these. So it's 2 of those. That's easy. 2 and 3 is 5 of them. One of these and one of those. Can't put those together. So now I got one of these plus one of those is, oh shit. But we all know, would we stop here?
No.
We would do work. Why can I do work here and I can't do it here? Because these are actually freaking numbers and maybe I could do something to them to make them like terms. The whole purpose of LCD is to make them like terms. Because if they were like terms, I could just put them together, yes? Now this one should be nice. And again, what's another name for LCD that we talked about already? It starts with the same 2 letters. LCM. LCM is LCD. What could they both multiply up to be? And that's an easy question, yes? What could they both multiply up to be? 21. So I'm getting a little ahead of myself in terms of what you would talk to your class about, but what does this need to become 21? A 7. And this needs a 3. Anytime these two are relatively prime, they need each other totally. Right? We talked about that relatively prime before. 3 and 7 are prime, so they're obviously relatively prime. So now what do I get? I get 7 over 21, yes? Plus 3 21s, which makes 10 21s. Okay, I like it. Right, and that's some basic fraction algebra that we kind of all know, and it gets worse when the numbers get bigger, of course, right? But now we've got some strategies we talked about before with LCM that will help us with that. All right, so let's come back. That's a little side note I wanted to throw in here, because basically what we did here was we did 1 over b plus 1 over b plus 1 over b a times. Yes? We took a steps of 1 over b. So I added 1 over b to itself a times. And if I add 1 to itself a times, it's a. Add 1 to itself 7 times. Don't you get 7? Right? Okay. So I kind of want to talk about this because we sort of inherently did that here. Okay. I like it. Okay, so let me become a little more formal here. This is all me. Well, this is in the book a little bit, yeah. But that's me over there. All right, so let me become a little more formal. Let's give a definition for what the shit a fraction is, as far as we determine it so far. So a fraction is a number that can be represented as A over B, where A and B are whole numbers, and what else must be true about B specifically?
Can't be 0.
It can't be 0. I love it. So that's any fraction would be the ratio of 2 whole numbers where the bottom is not 0. So we're still not allowing anything to be negative officially, because we haven't talked about negatives yet. Can you have a negative fraction? Of course. So eventually we'll have negative fractions. Is that cool? Does that make sense? That's just the straight up formal definition of what a fraction is. And the important thing here is can be represented as. Yes? So let me give you something in the future for us, but in the past for you, hopefully. How would you write that? Is that a fraction? Try you. Is that a fraction?
Yes.
Yes, it totally is. Why? Because if we represent it as what ratio? 1 over 10. Yes? Yes?
Mhm.
This is written in decimal form, but this is a fraction because it's 1/10. In fact, real quick, decimals are special fractions whose denominators are based on 10. That's why they fit in our number system, because our number system is based on 10. If our number system was based on 5, then this would be 1 over 5. Crazy shit. I like it. How are we doing so far? Okay, I like it. Blah, 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 blah. Does anyone remember about why this has got to be? What's up with that? What happens if that was 0?
So we divided.
It would be undefined.
Undefined. I love it. 6 divided by 3 is 2 because it takes 2 3s to make 6. 6 divided by 0 is the number that, when multiplied by 0, 6. No number is defined to do that. I love it. Okay. By the way, I'm just going to spew some more shit, and then I'm going to let you play with some manipulatives here in a minute, right? It's my job is spewing shit at you, I guess. Okay. So if you showed a child, one of your students, a young'un, this, and you say, how many are there? What would they say? Hopefully. 3, holy crap. They would say there's 3 objects there, right? 3 triangles, 3 whatevers. If you show them this and say, I'm going to be a little older now. So you could ask this question in a few different ways. You can kind of lead them. How many objects there are shaded?
Out of
Exactly, that would be the next part. So how many are shaded?
1.
1. Out of how many total objects?
3.
So this is actually another visual representation of 1/3. Okay, I like it. That's just a little side note again. The idea we were using before, like I used this earlier, yes, and what would this, pretend like those are equal. So what would this represent? 1/4, so pretend like they're equal. And then we had this shape here, and you could do blah, blah, blah. Oh yeah, pretend like those are equal. Chef cutting the pizza, oh jeez. And blah, 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 blah. Blah, blah, blah. What would that mean? 3 out of 8. Are there 8 total slices? So 3 out of 8 slices are left, maybe. I don't know. Okay. These are called region models. That's just what we call them. So any shape you choose to equally divide, that's called region modeling. Okay. And again, I'm not so concerned about the name, but you might as well know what those are called. Yeah, okay, so we sort of could have done this earlier. Let me do this. Create a region model. Let's see if we can do better, Jeff. Yeah, let's do this. Bam. Okay, so again, pretend like all the parts are equal. Okay. Superficially, what is this? 1/2, of course, right? And superficially, what's that? 2/4, yes? Now, we all know this is true. We all know what I'm talking about right now. But so if I took this picture and I just cut it, it would be this picture. So somehow, this number represents the same fractional piece as this number, and that's not surprising to us, because 2/4 does what? To become 1/2. It reduces,
Yeah.
right? So 2/4 is 2 over 2 times 2. Let me do 2 times 1 over 2 times 2, right? And real quick, I know I'm going to be really, incredibly enough, a math teacher is going to be detailed. What are the operations in here? What are the only operations in this
Division and
expression?
multiplication.
Sorry?
Division and
Yes,
multiplication.
yes, thank you. And division and multiplication are what kind of operations?
And it's.
It's kind of a weird, division and multiplication, they are opposites, right? Don't they kill each other? If I said, divide that in half, now double it, I'm done, right? Because those would cancel each other out. Exactly what happened, right? Now, this is really silly, but what's funny to me is people often forget that's what you're actually doing when you're reducing numbers. Okay. So any fraction that reduces means that the region model for the first fraction would be equivalent to the region model for its reduced version. So like what we did here. Okay. Let me see what's important here. Oh. Yeah, let's do this. Let's do this. I've been talking enough. So. Take a bag. Take a bag. Take a bag. And a bag. Okay. None of them have Easter candy in them, sorry. Bag. I like it. Well, this one's great. What's up? Oh, sorry. Oh, I'm sorry. I'm evil. You're like, what did I do to this guy? Okay. I think I pointed these out before, I can't remember. So we're gonna play them with them later. Hopefully everybody's got, let's make sure we got all the parts we need. So how many, everybody have green pieces? Green triangles?
Yeah.
What do you call the blue piece? Rhombus, I love it, or a kite. So rhombus is also known as a kite when it's this way. Okay. What about the red pieces? Trapezoid. What about the yellow piece?
Hexagon.
Hexagon, kick ass. Okay. Oh, let's see. Can you guys see, I'm pretty sure I pointed these shapes out before. Can you guys see which piece would we start with that we're going to break down, obviously? Hexagon, yeah. So let me take, here, I'll use this over. Let's focus on a hexagon. Come here. So, the red piece. If this is considered one whole piece, yes? What is the trapezoid, the red piece?
1/2.
Good. So you might want to write that down for yourself. So the yellow is a whole, is 1. Trapezoid represents 1/2, of course. Why? Because it's the number that it takes 2 of to make a whole. What about the rhombus?
1/3.
Yeah, can you guys get those on there? So it makes the, it's kind of neat. Right? Sort of looks like, for some reason it makes it look like an Autobot symbol. So there, it takes 3, so the rhombus is 1/3, trapezoid is 1/2, hexagon is 1, and of course, what about the little triangle dudes?
1/6.
1/6, yes. do a lot of stuff with these pieces. So, what does, so everybody's got that, you got a little note. What does that represent right there?
2/3.
2/3. Can you really quickly represent for me, what do I want to say here? Yeah, all right. Can you represent 2/6 for me with the triangles? All right, so there's 2/6. So there's 2/3 and there's 2/6. Hello? Now, how would you do 2/3 plus 2/6? What would you do?
Denominators equal.
No, we're not even thinking about it. We're purely thinking manipulative wise, just physically.
Put them on.
Isn't it when I do this right here, when I do this, shiboo, didn't I just add 1/3 plus 1/3?
Yeah.
That's how it makes 2/3. So now I've got this shape and I've got this shape. How do I add them together? Bam! Right?
Yeah.
And what does it equal?
1 whole.
1. I love it. Okay, cool. I want you guys to take a second. There's a connection you got to make for the students. But right now, this is just visually. We don't even know why. We don't know the make an LCD thing or reducing or anything yet. We just know visually that 2/3 plus 2/6 equals 1 whole. Now, can somebody explain to me why algebraically? What is 2/6?
1/3.
Yeah, so 2/3 plus 2/6 is 2/3 plus 1/3. 3/3, 1 whole. Yes?
Yep.
Is that cool? Okay, I like it. Now, okay. So, I mean, I could do, let's do one more example like that. So, put down on your desk 1/2 and 1/6. Now we got something more interesting here. So 1/2 and 1/6 would be,
1 red, 1 green.
I love it. Yeah, add those together. Think about what it's gonna take to do that. You could put them together and you got a little weird shape staring at you, right? What do you do with that?
It's like a chevron.
Why is it difficult to add these together? It's kind of a weird question, but if I had 1 blue and 1 blue, it's easy to add those together, correct? Because that'd be 1/3 plus 1/3 is 2/3. So these are difficult to add together. I can't really tell exactly what that is because they're not all the same. What can I do with the trapezoid? Break it down. Right? What does it take to make a trapezoid? 3 greens. So this is equivalent, yes? So now, 1/2 plus 1/6. Why is this easier now?
It's 4/6.
4/6, because I know every triangle is 1/6. So I got 1, 2, 3, 4. I got 4/6. Yes? Now, and I understand, this is kind of, what just happened? What we just did, how does it compare to algebra? I'm not even looking at it. Good job. Sorry, everybody at home. So let's write that down real quick. Write down the problem for me. 1/2 plus 1/6. What are you? Are you writable? Yes. So that was this. And we said that was equivalent to
4/6.
this. Turn that around. Plus this, yes? And what is this now?
3/6.
3/6. So what point does this make for students? Could I combine these easily and tell what the answer was based on what the shapes are? No, I couldn't, correct? So that explains 1/2 plus 1/6. It's not in the right form for me to combine them. What else, what other point does this make?
How many,
What did we have to make happen so that we could put them together?
breakdown?
Break them down, but specifically, how did we break it down? So it was the same denominator, right? All right. But I really desperately, we have the physical idea, it stands on its own. But we get to a point where just staring at the shape we get at the end doesn't really tell me something. I can't really identify it directly, yes? So then, but this represents a trapezoid. But now I could just say 1, 2, 3, 4, 6, which is what I would get here, yes? Okay, I like it. Now, and then I can make one more point with this, right? You do it, Jeff. Because what do we know we can do with 4, 6? We can reduce it. How would that look with this? What is this the shape of?
Oh. 1/3.
Isn't that the same thing? And that's the same thing? And what's this? 2/3. Did you guys all follow what just happened? And again, the whole purpose of manipulatives is to give them a different way to think about stuff, and then you relate it to the actual work you would do, right? Because the whole kinesthetic thing, playing around with shit, okay, they can do that. They love the hell out of that. Here, make this shape. No, yeah, I got you. And then you gotta, throw on top what we're actually doing algebraically. Okay, I like that. Algebraic. So, what's really neat is right now, what did I just do? Every 2 triangles became 1 rhombus, right? And do you see how that relates to what factor did I actually cancel to reduce this? Factor 2. Every group of 2 triangles became 1 rhombus. The factor of 2 shows up physically. That's crazy. Now, of course, you can't, holy shit. You can't, I got you, no worry. You can't do something like 3 11s plus 17 49s with manipulatives. Are you with me? My God, I don't even want to think about what 1 49th would look like. So you guys, by the way, do any of you guys have any other shapes in there besides? Okay, no, okay. Good. Because there are some other weird ass shapes that don't really go with these. Okay. Let me see, what else do I want to do with these? Oh, what about, okay. All right, so put down there for me 5 6 and 1/3. Put 5 6 and 1/3. How would you add those? Same kind of thing happens, right? In fact, I mean, you actually could sort of do something. This guy sort of fits in there. Right? But then I'm like more than a whole, yes? Exactly how much more? Well, we got the same issue, don't we? So if I break this guy up like this, it's in there.
You have 7.
What does that tell me?
7 6.
Yeah, so let me get this out of the way. Yeah, okay. Yeah, so I can look at this 2 different ways. So now let's bring some whole numbers into this. This is very much 7 6, correct? And again, this one, this time, what did I do? This time, this is kind of neat. Let me see if you guys agree with me at all. I think I have about I don't know how often people agree with me when I say it's neat. But this time, didn't I take that and break it by 2?
Yeah.
So that would be the same as
2 6.
doubling these. Yeah. So I get 5 6 plus 2 6. And then just visually, I know it's freaking 7 6 because every triangle is a 6th and I got 7 of them. You can't go wrong with that. Well, what's another way to represent this?
1
1 and 1/6. Let me put that together better. Now, real quick word about this. This is one of, if not the, most foolish decision of notation that mathematicians have ever done. This is remarkably stupid, right? Why? Why? Do you guys understand why? Yes.
It looks like you would multiply.
Yes. What did you do when you have two things sitting next to each other? You multiply them. What's hidden here? What is hidden between 1 and 1/6? Plus. Now, I don't know what we could have made it, but we could have done better than this shit, because one of the most fundamental things about math is when they're sitting next to each other, you multiply. And then we go, yeah, that looks good. What? Okay. So why do these match up? Why are those the same? Oh, sorry. I like it. Because, Jeff. No, go ahead.
Because there's one group, there's one.
No, so visually we can see why they match up, but computationally, why are these representing the same thing?
Because it would be like the
Go ahead, sir.
divisible unit and then the remnant.
I like it, you're doing exactly what I'm thinking. What would a whole thing be here? 6/6, so how much extra beyond a whole do we have? So one quick way to say why these are the same is this is 1/6 more than a whole, which is exactly what that says. What's the shortcut to convert a mixed number to what is this called? Improper fraction. I like it. It's improper. Okay, you guys hold up. You can take a look at it. What's the shortcut to make a mixed number into a improper fraction?
Multiply the whole number and then add.
Yeah, multiply what now?
The denominator with the whole.
6 times 1
And then add the top.
plus 1. Why? Why is that? I love it. Brendan's like, you didn't ask me. I just answered your question. Now I'm asking everyone. Why does that work?
You have 6 parts, and then you have an additional extra part.
Sure. What is 1 in terms of sixths? 6/6. In fact, I really want this to make sense. Whatever that is, that would be the same thing, right? If it's 1 in something. Okay. What if it was 2 in 1/6? This would have been 12/6. Yes? Okay, right? You guys with me? Which was 2 times 6. So that's why it's this times this, because that's what this needs to become over 6. And this would be the extra shit, because there's an understood plus in the middle. And of course, that's why the shortcut works. So I'm not saying do it that way, I'm saying that's why the shortcut works. So do the shortcut. Now looking at this guy, 7/6, can't I write this as 6 plus 1 over 6? And what's 6 divided by 6? And what's 1 divided by 6? I don't know. Right? Or you can just do long division if you want to. I'd rather do this. Right? You can always do this. Break the top down into a multiple of the bottom plus extra shit. That will always work. It's beautiful. In fact, that's the definition of division, to be honest. That's the remainder and all that kind of thing. Okay. Let me see. Trying to think about what order to do this in. Yeah, it's the same thing. Oh, we just did that. Okay, that's cool. And then we got weird little shit. So let me show you some. Oh, by the way, let's do this while we got this. Let me do one more thing with these pieces, and then I'll show you some videos with the kids doing some math for the guy. How would I do? This should feel very familiar to you. Can you please represent 5/6? We've already done that once. Easy enough. Now let's say I want to subtract 1/3 from that. There's several different ways to do it. And again, you don't have to think computationally what you would do, you can actually completely think visually, right? So I got 5, 6, and I want to take away 1/3.
You would take 2 6.
Yeah, exactly. So what would a student think? What the student who's doing the manipulatives, what piece represents 1/3?
To take out 2 of the
Yeah,
triangles.
good, because 2 triangles is equivalent to. So what the student could do with their hands is they can take what 1/3 is and find it. Now think about this. Didn't we do this when we learned about subtraction? And in a circle of 9 things, and then you're supposed to subtract 5 away. Don't you just find 5 and take them out? Isn't this kind of exactly that? We found a group of stuff that represents what I'm taking away. So if I take that away, I'm left with 1/2. Now, we totally did that problem visually, but now let me catch up with what people were saying. What would this do? What would I do mathematically to do this problem?
Multiply by 2.
Good. So now I got 5, 6 minus 2, 6, which is 3, 6, which is 1/2. All right, sweet. Okay. I like it. I really hope you guys, no, I haven't said this in a while, but if I ever do something that doesn't make sense, immediately stop me and say, what the shit did you just do, right? What's really important right now is, I know a lot of you guys don't like fractions, but I know if pushed, you could do fractional work. Especially with fractions like 5, 6, and 1/3. Right, so when it becomes 11 over 87 plus 2 over 39, it's like, you go, shit. Yes? Oh. So, but the big part, what I want you to take away from this is, the younger the age you get to work with, the more manipulatives you're gonna use, obviously, right? And when you're using manipulatives, what's important is to let them play with the manipulatives, let them play, and then try to organize, and then try to relate it, of course, to this, because your purpose is to let them get to a point where they don't have to play with manipulatives. I don't want somebody sitting in my calculus class putting this together to do some fraction work. I'm almost there, Mr. Wall. Right? Anyway, that's kind of silly, but you know what I mean. We're trying to get them to be there without relying on this, but this sets the foundation in their brain to understand what that means, even if they're doing 11 over 80. Can you picture in your head something that would represent 11 over 80? Can somebody tell me, right? Can you picture 1/2? Wouldn't that be, couldn't you do a box that's cut in half?
Yeah.
And then shade one of them. Woohoo! What would 11 over 80 be? Who's got a picture in their head of 11 over 80?
80 holes with 11 things inside of each hole.
Okay, so the
hole.
shading is related to putting stuff in the hole,
Yeah.
okay? So 80 holes with 11 things, sure, all right. That'll work. So I'd say what fractional part of this group of holes is filled in? Okay, sure, 11. That works. You thinking golf, or I don't know what the, okay.
Flags.
All right. But, or you could think of a circle broken into 80 parts, right? I mean, this is an insane person cutting a pizza. You get 1/80th of a pizza. Oh, thank you so much. You know, it's like you can floss your teeth and buy pizza. Right? And then you have 11 of them, somebody ate. Right? So you say 11 out of 80 of the pizza's gone. Does that make, I mean, okay. But that's not something you want to try to do with manipulatives. But you've got the image in your head. You can pull it up anytime you want to. You know that's what these are based on. And you want them to have that same foundation. So actually getting to play with some shit to have that foundation to call back. Okay. Let's see. Oh, let me show you some videos of little people being forced to do work. Sounds exciting. Yeah, turn you off. Copyright business.